Close your eyes for a moment and imagine standing beneath a truly dark sky, miles from the nearest city, far from the artificial glow that obscures the heavens. Above you, stretching from one horizon to the other like a luminous river frozen in the darkness, lies the Milky Way. That pale, ethereal band has captured human imagination for millennia, inspiring myths and legends across every culture that has ever gazed upward into the night. Ancient Greeks saw it as milk spilled from the breast of the goddess Hera, a cosmic accident that painted streaks of light across the heavens. Norse mythology described it as the pathway to Valhalla, the road along which fallen warriors would tread among the stars to reach their eternal reward. Chinese astronomers called it the Silver River, a celestial waterway flowing through the darkness, separating lovers across an impossible distance. The indigenous peoples of Australia saw it as a river in the sky, while various African cultures interpreted it as the backbone of the night itself. Tonight, we embark on a journey through our galactic home, exploring 100 fascinating truths about this magnificent cosmic structure that we call the Milky Way Galaxy. We live inside a barred spiral galaxy. This simple statement contains profound implications that humanity took thousands of years to fully grasp and accept. The Milky Way is not merely a backdrop to our existence, not simply a pleasant pattern of lights decorating the night sky, but our cosmic neighborhood, our galactic home, the vast structure within which everything we know has emerged and evolved. When you look up at the night sky on a clear, moonless evening and see that misty band of light stretching overhead, you are looking at the combined glow of billions upon billions of stars, all of them part of the same massive gravitational structure that contains our sun, our solar system, our tiny planet Earth, and everything we can possibly see with our naked eyes from our vantage point on this small world. The Milky Way spans approximately 100,000 light-years from edge to edge, according to widely accepted measurements of its luminous disk. Though different measurement techniques yield somewhat varying results, with some studies suggesting the visible disk measures closer to 87,000 light-years across, while the dark matter halo extends much farther. This distance is so vast, it defies easy comprehension. To truly grasp this measurement requires understanding that 1 light-year, the distance light travels in a single year, equals approximately 5.88 trillion miles, or 9.46 trillion kilometers. Light itself, moving at 186,282 miles per second, the fastest speed possible in our universe, requires a full 100,000 years to traverse the galactic disk from one side to the other. These numbers strain human comprehension, existing on scales so far beyond our everyday experience that our minds struggle to properly visualize them. If you could somehow board a spacecraft capable of traveling at 1% of light speed, which would represent an achievement far beyond our current technology, it would still take you 10 million years to cross from one edge of the galactic disk to the other. If that spacecraft could somehow sustain you for that impossible journey, you would watch 10 million years pass, see thousands of generations live and die, witness the rise and fall of entire civilizations, all while crossing a single galaxy. Within this vast cosmic structure, somewhere between 100 billion and 400 billion stars shine and burn, each following its own unique orbit around the galactic center. This enormous range in the estimate, spanning a factor of 4, reflects the genuine uncertainties involved in counting stars throughout such an immense volume of space, particularly given that we observe the galaxy from within, rather than from some external vantage point. But even the lower estimate of 100 billion stars represents a number almost beyond imagination, a quantity that defies our ability to truly comprehend it. If you could somehow count 1 star per second without stopping for rest, food, sleep, or any other interruption, maintaining a perfect pace day and night without pause, it would take you more than 3,000 years just to reach 100 billion. You would need to count through the entire span of recorded human history, and then continue for hundreds of years beyond that. Our solar system occupies a relatively quiet neighborhood, approximately 26,000 to 28,000 light-years from the galaxy's center, though some measurements place this distance closer to 25,000 light-years, or up to 27,000 light-years, depending on the precise method used. This positioning is neither in the crowded, chaotic heart of the galaxy, where stars pack densely together and the environment seethes with radiation, nor in the sparse, lonely outer reaches, where stars are few and far between, and the sky would appear nearly empty. Instead, we reside in a middle zone, a region of moderate stellar density, where conditions have remained stable enough, calm enough, predictable enough for life to emerge from chemistry, to evolve from simplicity to complexity, and eventually to produce beings capable of contemplating their place in this vast cosmos. This favorable location places us within a minor spiral arm called the Orion Spur, also known as the Orion Arm or the Local Arm, a structure approximately 10,000 light-years long that extends between the galaxy's major spiral arms like a bridge or connecting branch. The Orion Spur contains conspicuous astronomical features, including the Cygnus Rift, a dark lane of obscuring dust visible cutting through the summer Milky Way, and the brilliant Orion Nebula, a stellar nursery approximately 1,344 light-years away that shines brightly enough to be visible to the naked eye as a fuzzy patch in the sword of Orion. Whether the Orion Spur represents a truly separate arm or merely a branch connecting to one of the major arms remains under investigation, with some researchers suggesting it may actually be part of the Perseus arm, though this connection has not yet been definitively established through observational evidence. We orbit the galactic center at approximately 515,000 miles per hour, or roughly 828,000 kilometers per hour, though measurements vary slightly depending on the specific method used and the reference frame chosen. Despite this tremendous velocity, which is more than 1,000 times faster than a commercial jetliner, more than 20 times faster than the escape velocity from Earth, the scale of the Milky Way is so incredibly vast that completing one full orbit takes between 225 and 250 million years. Astronomers sometimes call this period a galactic year or cosmic year, and it provides a useful timescale for measuring and contextualizing events in Earth's geological and biological history, offering a cosmic calendar against which we can mark the major milestones of our planet's story. Since our planet Earth formed approximately 4.6 billion years ago, condensing from the swirling disk of gas and dust that surrounded the young sun, the solar system has completed roughly 18 to 20 galactic orbits, circling the galaxy again and again as continents shifted, oceans formed and dried, life emerged from the primordial seas, evolved through countless forms, survived 5 major extinction events, and eventually produced beings capable of calculating exactly how many times they had circled this cosmic carousel. When the last non-avian dinosaurs walked the Earth 66 million years ago, just before the catastrophic asteroid impact that would end their reign, the solar system had completed approximately 1/4 of its current orbit. Our position in the galaxy has changed. The stars surrounding us have shifted. The cosmic neighborhood has transformed, all while remaining part of this same vast galactic structure. The Milky Way itself is ancient beyond easy comprehension, its age measured not in millions, but in billions of years. Current research, drawing on evidence from globular cluster ages, stellar evolution models, and cosmological simulations, indicates our galaxy began forming approximately 13.6 billion years ago, less than a billion years after the Big Bang created the universe itself, some 13.8 billion years ago. This means the Milky Way has existed for nearly as long as the universe has allowed structures like galaxies to exist at all, forming in the relatively brief window after the cosmic dark ages, when the first stars began to shine, assembling from smaller clumps of dark matter and gas, growing through mergers and accretion, evolving into the magnificent spiral structure we observe today. Over those billions of years, the galaxy has grown through the accretion and consumption of smaller galaxies that ventured too close, survived multiple major cosmic collisions that sent shockwaves through its structure, and continuously formed new generations of stars from the raw materials of hydrogen and helium left over from the Big Bang, gradually enriched over time with heavier elements forged in the nuclear furnaces of stellar cores and scattered through space by supernova explosions. The galaxy we see today represents billions of years of evolution, a structure shaped by gravity, enriched by stellar nucleosynthesis, sculpted by collisions, and still dynamically evolving before our eyes. Understanding our galaxy's true nature was a gradual process in human history, spanning centuries of careful observation and theoretical insight. For thousands of years, observers noted the pale band across the sky, but could not discern its fundamental nature or what it truly represented. In 1610, Galileo Galilei pointed his newly invented telescope toward the Milky Way and made a revolutionary discovery. The luminous band was not a continuous glow or celestial substance, but rather the combined light of countless individual stars, so numerous and distant that they blurred together when viewed with the naked eye, their individual points of light merging into a continuous glow. This observation fundamentally changed how humanity understood the cosmos, suggesting that space was far more vast, far more populated, far more complex than anyone had previously imagined. Yet even after Galileo's groundbreaking discovery, the true nature and scale of the Milky Way remained deeply mysterious to astronomers and philosophers. Were these stars part of a finite collection, an island of light floating in an otherwise empty universe? Or was the cosmos filled with such collections, perhaps infinitely many of them scattered throughout space? These questions sparked intense debates that lasted for centuries, with thinkers proposing various models and cosmologies to explain the observations. In 1755, the philosopher Immanuel Kant, working from first principles and philosophical reasoning rather than detailed observations, proposed that the Milky Way was a rotating system of stars held together by gravity, similar to the solar system but operating on an incomprehensibly larger scale. He further suggested, with remarkable prescience, that other nebulous patches visible in the night sky through telescopes might be separate island universes, each containing their own multitudes of stars, existing far beyond the boundaries of our own galactic system. Kant's prescient speculation proved remarkably correct, though it took nearly 2 centuries for technology and observational techniques to advance sufficiently to confirm his ideas. The breakthrough came in the 1920s, when Edwin Hubble, using the 100-inch Hooker telescope at Mount Wilson Observatory in California, the largest and most powerful telescope in the world at that time, measured the distance to the Andromeda Nebula using Cepheid variable stars as distance indicators. He found that Andromeda lay far beyond the boundaries of the Milky Way as it was then understood, proving conclusively that it was indeed a separate galaxy. This discovery, announced in 1924 and building on observations made in 1923, revealed that the universe contained not just one galaxy, but countless galaxies, each potentially hosting billions of stars, each an island universe in its own right. The cosmic scale suddenly expanded exponentially in human understanding, transforming our conception of the universe from a single galactic system to an infinite expanse populated by countless galaxies. The word galaxy itself derives from the Greek galaxias, meaning milky, referring specifically to the Milky Way's appearance as a pale band of light across the night sky. When ancient Greek astronomers looked up and saw this luminous river, They gave it a name that reflected its milk-like appearance, and that name has echoed through history, eventually being applied to all similar cosmic structures discovered throughout the universe. Every galaxy we observe today, from the nearest dwarf irregulars to the most distant spirals visible only to the most powerful telescopes, shares a name derived from our own galaxy's ancient Greek designation. From our vantage point within the galaxy's disk, observing from inside the structure rather than viewing it from some external perspective, we cannot easily see the Milky Way's overall architecture and shape. Imagine trying to map a vast forest while standing among the trees, with thick fog limiting your vision to just a few dozen yards in any direction, and you begin to understand the challenge astronomers face when studying the Milky Way's structure. We must piece together its architecture using indirect observations, measuring the positions and motions of individual stars one by one, mapping clouds of gas and dust through their radio emissions and infrared glow, studying the distribution of radiation that permeates space, and slowly building up a three-dimensional picture from thousands of individual measurements. The Sun sits approximately 95 light-years above the galactic plane, positioned just slightly north of the disk's midline, above the densest concentration of stars and gas that defines the thin disk. This relatively central location within the disk's thickness, neither far above nor far below the galactic plane, explains why we see the Milky Way as a band encircling the entire sky, rather than concentrated in one particular direction. If we were positioned significantly above or below the disk, floating in the halo perhaps 10,000 or 20,000 light-years from the disk plane, we would have a magnificent panoramic view of the entire spiral structure spread out below us, able to see the spiral arms traced out by bright blue stars, able to observe the bar stretching through the central regions, able to witness the galaxy's full glory in a way impossible from our current embedded perspective. The galaxy's visible structure can be divided into several distinct regions, each with characteristic properties that reflect different aspects of the galaxy's formation history and current dynamics. Understanding these components, how they differ from each other, how they formed, and how they interact, provides crucial insights into galactic evolution and the processes that shaped our cosmic home. The thin disk, where our Sun resides along with most of the galaxy's current star formation, spans approximately 1,000 to 2,000 light-years in thickness, forming a relatively flat structure like a cosmic pancake where most stellar birth currently occurs. Within this thin disk, stars move in orderly, nearly circular orbits, all rotating in the same direction around the galactic center, like horses on a cosmic carousel, their motions organized and predictable. This organized motion reflects the disk's formation from a rotating cloud of gas that gradually settled into a flat configuration, losing energy through collisions and interactions, but conserving angular momentum, spinning faster as it contracted, eventually forming the thin, rotating disk we observe today. Above and below the thin disk lies the thick disk, a more vertically extended structure reaching to heights of approximately 4,000 to 6,000 light-years above and below the galactic plane. The thick disk formed earlier in the galaxy's history, primarily between 10 and 13 billion years ago, during a more chaotic and violent period when the young Milky Way was still actively accreting material from its surroundings and experiencing frequent collisions with smaller protogalactic fragments. Stars in the thick disk are generally older, more metal-poor than their thin disk cousins, containing lower abundances of elements heavier than helium, and their orbits show greater random motion, carrying them to higher altitudes above and below the galactic plane in their journeys around the galactic center. At the galaxy's heart lies the central bulge, a dense, roughly spherical concentration of mostly older stars spanning approximately 10,000 light-years in diameter, dominating the galactic center region with its densely packed stellar population. However, Detailed observations and analysis have revealed that what astronomers initially interpreted as a classical bulge is actually something called a pseudobulge, a structure formed through different processes than traditional bulge formation theory would predict. This pseudobulge formed through the growth and evolution of the galaxy's central bar, rather than through the violent mergers and collapse that created classical bulges in other galaxies, and it appears peanut-shaped or box-shaped when viewed from certain angles, a consequence of the complex three-dimensional structure created by the rotating bar and the orbital patterns it induces in stars. The central bar itself stands as one of the Milky Way's most prominent and dynamically important features, though paradoxically it remained hidden from human observers for most of our history, obscured by dust in the galactic plane. This elongated structure, consisting of densely packed older stars mostly formed billions of years ago, extends approximately 27,000 light-years from end to end, though different measurement techniques and definitions yield slightly varying estimates of its precise dimensions. The bar rotates as a coherent structure, spinning like a solid object even though it consists of millions of individual stars, and its powerful gravitational influence shapes the orbits of stars and gas throughout the inner galaxy, funneling material toward the center, influencing spiral arm structure, and fundamentally affecting the galaxy's evolution and dynamics. Bars like the Milky Ways are common features in spiral galaxies throughout the universe, appearing in roughly 2/3 of all spiral galaxies observed by modern surveys. They play crucial roles in galactic evolution, acting as cosmic highways that transport gas from the outer disk toward the central regions, where it can fuel star formation and feed the central supermassive black hole, potentially triggering enhanced activity in the galactic nucleus. The Milky Way's bar likely formed within the last few billion years through instabilities in the rotating disk, a process that computer simulations suggest is a natural consequence of disk evolution in galaxies with sufficient mass and specific rotational properties. Extending outward from the ends of the bar are the spiral arms, those magnificent curved structures that give spiral galaxies their distinctive and beautiful appearance, creating the pinwheel patterns that have captivated astronomers since they first observed spiral galaxies through telescopes. Current evidence, drawing on multiple observation techniques, including radio mapping of molecular clouds, infrared surveys of stellar populations, and studies of masers marking regions of active star formation, indicates the Milky Way has two major spiral arms, the Perseus arm and the Scutum Centaurus arm, each stretching tens of thousands of light-years through the galactic disk. These major spiral arms contain significantly higher densities of gas, dust, and young, luminous stars compared to the regions between them, creating the bright, sweeping curves visible in face-on images of other spiral galaxies, highlighting the arms through the brilliant blue light of young, massive stars. The enhanced density in spiral arms triggers increased star formation, as gas clouds compressed by the arm's gravitational field fragment and collapse to form new stellar generations, creating the association between spiral arms and bright young stars that astronomers use to trace spiral structure in both the Milky Way and external galaxies. The spiral arms are not solid structures that rotate rigidly like the spokes of a wheel, but rather density waves, regions of enhanced density that propagate through the disk like ripples moving across the surface of a pond. Stars and gas clouds move through the arms, entering regions of higher density from one side, slowing down as they experience enhanced gravitational forces in the denser environment, and then exiting from the other side to continue their orbits, speeding up again as they return to the inter-arm regions. This density wave phenomenon, first proposed in the 1960s by astronomers C. Lin and Frank Hsu, elegantly explains how spiral patterns persist over billions of years despite differential rotation, which would otherwise wind spiral arms up tightly, like thread on a spool, and destroy the spiral pattern within a few 100 million years. As gas and dust enter a spiral arm, compression waves triggered by the enhanced gravity raise the density and pressure of molecular clouds, causing them to become gravitationally unstable and fragment into collapsing cores that form new stars, particularly massive, luminous blue stars, whose intense radiation and powerful stellar winds further compress surrounding gas, potentially triggering additional star formation in a self-propagating process. These massive young stars live fast and die young, burning through their nuclear fuel in just a few million years and exploding as supernovae before they can drift far from their birth sites, which keeps the spiral arms bright and prominent, continuously highlighted by fresh generations of blue giants even as older stars drift away into the inter-arm regions. Spiral arm pitch angles, which define the angle between a spiral arm and a circle around the galactic center, range from approximately 7 to 25 degrees throughout the disk, depending on which arm you're measuring and at what galactic radius. Different arms may have different pitch angles, and the angles may change with distance from the galactic center, reflecting the complex and dynamic nature of spiral structure, the influence of the rotating bar, and the effects of resonances where orbital frequencies match the spiral pattern speed. Smaller pitch angles produce tightly wound spirals where arms curve dramatically, wrapping around the galaxy multiple times, while larger angles create more open, sweeping patterns where arms extend outward more directly. Recent observations have revealed additional structures within the Milky Way beyond the major spiral arms, adding complexity to our understanding of galactic architecture. The near 3 kiloparsec arm was discovered in the 1950s through radio observations, located approximately 10,000 light-years, about 3 kiloparsecs, hence its name, from the galactic center along our line of sight, expanding outward from the central regions. The far 3 kiloparsec arm was discovered much more recently, in 2008, using radio telescope observations of carbon monoxide gas that traces molecular clouds. This arm appears shorter than the major arms and lies along the bar, expanding away from the central bulge at velocities exceeding 50 kilometers per second, suggesting it may be material being driven outward by the bar's rotation and gravitational influence. Beyond the visible disk and bar, beyond the regions where stars shine brightly and gas clouds form new stellar generations, lies the stellar halo, a roughly spherical distribution of stars extending hundreds of thousands of light-years from the galactic center in all directions. The halo contains relatively few stars compared to the disk, perhaps only a few % of the galaxy's total stellar population, making it a diffuse, sparse region where stars are separated by vast distances. Yet these halo stars are among the oldest in the galaxy, ancient survivors from the Milky Way's earliest days, and their properties and distributions provide crucial clues about how the galaxy formed and evolved over cosmic time. Halo stars follow highly elliptical orbits at all inclinations, plunging through the disk and central bulge like comets swooping through the solar system, then rising to great heights above the disk plane before falling back down, their paths carrying them through radically different galactic environments as they complete their long looping trajectories around the galactic center. Some halo stars orbit in the same direction as the disk, while others orbit retrograde, moving against the galaxy's overall rotation, their unusual orbital properties reflecting their origins in smaller galaxies that merged with the Milky Way billions of years ago, each contributing stars with distinctive orbital patterns that persist to the present day. The halo also hosts approximately 150 to 200 known globular clusters, spectacular dense spherical collections of hundreds of thousands to millions of stars bound together by their mutual gravity, each cluster shining like a compact swarm of stellar bees. These clusters are among the most ancient objects in the Milky Way, with ages reaching 12 to 13 billion years, formed in the galaxy's youth when the universe itself was only a billion or 2 years old. Their existence places a firm lower limit on the galaxy's age, since the galaxy must obviously be at least as old as its oldest stars, and studies of globular cluster populations, their ages, compositions, and spatial distributions provide powerful constraints on models of galaxy formation and early galactic evolution. The oldest individual stars in the Milky Way, found both in globular clusters and scattered throughout the stellar halo, approach 13 billion years in age, ancient beyond easy comprehension. These metal-poor stars formed when the universe was less than a billion years old, when the Milky Way was just beginning to take shape, when the first generations of galaxies were assembling from smaller fragments, when conditions throughout the cosmos were profoundly different from what we observe today. They have witnessed nearly the entire history of the galaxy, seeing it grow from a collection of protogalactic clumps into the magnificent spiral we observe today. The Milky Way is not a static, unchanging structure frozen in time like a museum exhibit or photograph, but rather a dynamic, evolving system that continues changing even as we observe it. The galaxy experiences a slow, breathing motion, with the disk oscillating up and down as it rotates, creating vertical waves that ripple through the stellar distribution. This warping of the disk results from tidal interactions with satellite galaxies, particularly the large and small Magellanic Clouds, whose gravitational influence tugs on the Milky Way's outer regions, and from the torque exerted by misalignment between the disk's rotation axis and the orientation of the dark matter halo, creating stresses that manifest as vertical oscillations and warping of the disk plane, particularly pronounced at the galaxy's outer edges, where the disk's self-gravity is weakest and external influences can have proportionally greater effects. At the very heart of the Milky Way, buried behind dense clouds of gas and dust that block visible light and hide the galactic center from optical observation, lurks something extraordinary, something that represents one of the most extreme environments in the entire galaxy. This is Sagittarius, a star, a supermassive black hole possessing a mass approximately 4.297 million times that of our Sun. All of that tremendous mass compressed into a region smaller than the orbit of Mercury around the Sun, creating a gravitational field so intense that space-time itself becomes drastically warped, bent into configurations that would seem impossible anywhere else in the galaxy. This cosmic behemoth represents one of the most extreme objects nature can create, a place where our everyday understanding of physics breaks down, and Einstein's general theory of relativity must be invoked to properly describe what occurs. Black holes form when matter becomes so densely compressed that its gravity overwhelms all other forces, including the nuclear forces that normally prevent complete collapse, causing total gravitational collapse into a singularity surrounded by an event horizon. The result is a region of space-time where gravity is so incredibly intense that nothing, not matter, not radiation, not even light itself, can escape once it passes the boundary called the event horizon, the point of no return beyond which everything is inexorably drawn into the black hole's depths. Because light cannot escape from within the event horizon, black holes are literally black, completely dark, invisible against the darkness of space itself, earning their evocative name. We can only detect them indirectly, by their gravitational effects on surrounding matter, by the radiation emitted by materials spiraling toward them before crossing the event horizon, by the motions of nearby stars whose orbits reveal the presence of a massive, invisible gravitating body, by the distortion of light from background objects whose trajectories are bent by the black hole's intense gravitational field, and through other subtle effects that reveal the monster's presence even though the monster itself remains hidden. Sagittarius. A star was discovered in 1974 by astronomers Bruce Ballack and Robert L. Brown during radio observations of the galactic center, part of a broader survey to map radio emission from the innermost regions of the galaxy. Working at the National Radio Astronomy Observatory in Green Bank, West Virginia, they detected an unusual compact radio source at the exact center of the galaxy, a powerful emitter that appeared point-like even at the highest available resolution. The asterisk in its name, that small star-shaped symbol after the A, was added in 1982 by Brown, who recognized that the strongest radio emission from the galaxy's center appeared to originate from a very compact, non-thermal radio source embedded within a larger, more diffuse radio region known as Sagittarius A. The asterisk distinguished this special compact source from the larger region it inhabited, marking it as something unique, something worthy of particular attention. Over subsequent decades following its discovery, astronomers monitored stars orbiting this radio source, patiently tracking their motions year after year, using those stellar orbits as cosmic laboratories to probe the nature and properties of the object they encircled. By carefully measuring stellar positions and velocities, they could use Newton's and Einstein's laws of motion and gravity to determine the mass of whatever object lay at the center of those orbits, and the answer consistently pointed toward a supermassive black hole. The breakthrough observations came from two research teams, led by Reinhard Genzel working in Europe and Andrea Ghez working in California, who spent decades tracking stars in tight orbits around Sagittarius A star, accumulating data with ever-improving instrumentation, building an ironclad case for the black hole's existence. For this groundbreaking work, decades of patient observation and analysis that established beyond reasonable doubt the existence of a supermassive black hole at the Milky Way's center, Genzel and Ghez shared the 2020 Nobel Prize in Physics, recognized by the scientific community for providing some of the most compelling evidence yet obtained for the existence of supermassive black holes, those cosmic giants that lurk at the centers of most galaxies. The star designated S2, one of the brightest stars orbiting close to Sagittarius star, and therefore one of the easiest to track precisely, provides particularly compelling evidence for the black hole's presence and properties. This star orbits the black hole with a remarkably short period of just 16 years, an incredibly rapid orbit by galactic standards, completing a full circuit in less time than it takes Neptune to orbit our Sun once. At its closest approach to the black hole, a point in its orbit called periastron, S2 comes within approximately 11 billion miles, about 120 astronomical units, a distance that sounds vast by everyday standards, but is extraordinarily close by galactic scales, bringing the star within reach of the black hole's intense gravitational field. At this closest approach, S2 reaches velocities of approximately 3% of the speed of light, or about 17.1 million miles per hour, moving fast enough that relativistic effects become measurable and important. At these tremendous speeds, time dilation becomes observable. The star's light becomes redshifted by the black hole's gravity, and the star's orbit deviates measurably from simple Keplerian predictions, showing relativistic precession that provides additional evidence for the black hole's presence and tests Einstein's general theory of relativity in extreme gravitational conditions. By applying Kepler's laws of orbital motion to S2 and numerous other stars tracked over decades of observation, researchers could precisely calculate the mass of the object they orbited, and the conclusion was inescapable: Sagittarius. A star had to be a black hole, with millions of solar masses concentrated in a region too small to be anything else. In May 2022, the Event Horizon Telescope collaboration released the first image of Sagittarius A star, a historic achievement that provided visual confirmation of the black hole's existence, transforming it from an invisible presence inferred from stellar motions into something we could actually see, or at least see the immediate environment surrounding. This image represented the culmination of years of work involving hundreds of scientists and 8 radio telescopes around the world, working together in perfect synchronization to capture radio waves from the galactic center, combining their data to create an image with unprecedented resolution. The event. Horizon Telescope is not a single instrument, but a remarkable global network of radio telescopes spanning from Hawaii to Antarctica, from Arizona to Spain to the South Pole, working together through a technique called very long baseline interferometry to form a virtual telescope the size of Earth itself. This planetary scale instrument achieved the angular resolution necessary to image the immediate environment around the black hole's event horizon, distinguishing features just a few times larger than the event horizon itself, resolving structure on angular scales of about 20 microarc seconds, equivalent to reading a newspaper in New York while standing in Los Angeles, or seeing a donut on the moon from Earth. The image shows a bright ring of glowing gas and dust surrounding a dark central region, exactly the signature astronomers expected to observe if a supermassive black hole lurked at the galactic center. This dark region, called the shadow, is not the event horizon itself, but rather the larger area where the black hole's immense gravity has bent and captured light rays, preventing them from escaping to reach our telescopes, creating a dark silhouette against the bright background emission. The shadow's size, approximately 52 microarc seconds across, matches theoretical predictions for a black hole of Sagittarius A's mass remarkably well, providing additional confirmation that we are indeed observing a black hole rather than some other exotic object. The bright ring visible in the image represents radiation from superheated material spiraling toward the event horizon at tremendous speeds, forming what astronomers call an accretion disk or accretion flow. This material, drawn inward by the black hole's irresistible gravity, heats up through friction, compression, and magnetic effects to temperatures of millions or even billions of degrees, causing it to emit intense radiation across the electromagnetic spectrum, from radio waves to X-rays. The glowing matter traces out the region just outside the event horizon, revealing the structure of space-time around the black hole and providing a window into one of nature's most extreme environments. Creating this image proved extraordinarily challenging, far more difficult than imaging M87 star, the first black hole ever photographed by the Event Horizon Telescope in 2019. While M87 star is far more massive, containing more than 1,500 times Sagittarius A star's mass, making it one of the most massive black holes known, it is also much more distant, lying about 55 million light-years away, so it appears roughly the same angular size in the sky as Sagittarius, a star despite the vast difference in physical size. However, M87 star proved relatively stable, with its appearance changing only slowly over hours and days, allowing astronomers to observe it over extended periods and combine multiple observations to build up a clear image. Sagittarius, a star by contrast, is highly variable, with its appearance changing dramatically on timescales of just minutes to hours, flickering and fluctuating as hot spots of gas orbit the black hole every few minutes, constantly altering the distribution of bright emission and making it extraordinarily difficult to create a stable image. This variability arises because matter orbits faster around smaller black holes, following Kepler's laws, which dictate that orbital periods decrease with the mass of the central object. At Sagittarius, a star, hotspots of superheated gas circle the event horizon, completing full orbits in mere minutes, far faster than the hours-long observations needed to collect sufficient data for imaging, creating a constantly shifting target that changed appearance faster than it could be photographed. To overcome this challenge, the Event Horizon Telescope team developed sophisticated new imaging algorithms, that could reconstruct a consistent picture from rapidly changing observations, essentially creating an averaged image that captures the black hole's typical appearance rather than any single moment in time. They combined data from multiple observation sessions, developed new techniques to account for the variability, and created thousands of simulated images to test their reconstruction methods, eventually producing the image released in 2022 that showed the world what Sagittarius A star truly looks like. In March 2024, the Event Horizon Telescope revealed another breakthrough, the first image of Sagittarius, a star in polarized light, opening a new window into the black hole's magnetic environment. Light becomes polarized when its electromagnetic waves align in a particular direction, which can occur when light passes through magnetized plasma, scatters off particles, or passes through strong magnetic fields. The polarized light image revealed organized magnetic field structures spiraling around the black hole, twisted and stretched by the rotating space-time, creating patterns that resemble iron filings arranged around a bar magnet, but operating on vastly larger scales and involving magnetic fields billions of times stronger than Earth's magnetic field. These magnetic fields, revealed in the polarized light observations, appear remarkably similar to those observed around M87 star, suggesting that strong, organized magnetic fields may be a universal feature of supermassive black holes, regardless of their size or the properties of their host galaxies. This similarity is particularly intriguing because M87 star is known to produce a prominent relativistic jet, a narrow beam of particles and radiation shooting outward from the black hole at nearly the speed of light, extending thousands of light years into space. The magnetic field structures play crucial roles in jet formation and collimation, channeling energy and matter into narrow beams, raising the intriguing possibility that Sagittarius A star might also harbor a hidden jet, perhaps weaker or oriented differently than M87 stars, but operating through similar physical mechanisms. Recent research has determined that Sagittarius A star is spinning rapidly, rotating with an angular velocity about 60% of the maximum possible value for a black hole of its mass, approaching but not quite reaching the theoretical maximum spin rate allowed by general relativity. This rapid rotation causes the space-time immediately around the black hole to become profoundly distorted, dragged along by the black hole's rotation in an effect called frame dragging or the lens-thirring effect. Near a rapidly spinning black hole, space-time itself rotates, forcing everything near the event horizon to move in the direction of the black hole's spin, whether it wants to or not, creating a region called the ergosphere where remaining stationary becomes physically impossible. The spinning black hole's influence on surrounding space-time can be visualized as an oblate ellipsoid, somewhat flattened like a football when viewed from the side, compressed along the rotation axis and extended at the equator. This shape affects how matter flows toward the event horizon, how energy can be extracted from the black hole's rotation through processes like the Penrose mechanism or the Blandford-Znaeck process, and how relativistic jets might form and be accelerated to near light speed. The black hole's spin, measured through observations of its effects on surrounding matter and the shape of the shadow it casts, provides crucial information about its formation history and evolution over billions of years. Despite its tremendous mass of 4.297 million suns, Sagittarius A star is remarkably quiet by supermassive black hole standards, consuming material at a rate far below what its gravitational reach would allow. The black hole accretes very little material, with less than 1% of the gas that falls within its gravitational sphere of influence actually crossing the event horizon to be consumed. Most captured gas is ejected as outflows, blown back out by radiation pressure, magnetic force, and turbulence in the accretion flow before it can fall irretrievably into the black hole, creating an inefficient feeding process that keeps Sagittarius A star relatively dim. This inefficiency in accreting matter explains why Sagittarius A star emits relatively little radiation compared to actively feeding supermassive black hole holes in other galaxies, some of which become brilliant quasars that outshine all the stars in their host galaxies combined, beaming radiation across billions of light years of space. Sagittarius. A star is essentially starving, existing in a low luminosity state despite being surrounded by stars and gas, and this quiescence represents a common state for supermassive black holes in present-day galaxies, most of which have exhausted the abundant gas supplies available in the early universe and now merely sip at the sparse material still falling toward them. The region immediately surrounding Sagittarius hosts extraordinary stellar populations that experience conditions found nowhere else in the galaxy. The galactic center contains stellar densities reaching approximately 10 million stars per cubic parsec in its innermost regions, compared to just 1 star per cubic parsec in our solar neighborhood, creating an environment where stars are packed together thousands of times more densely than in the disk regions where our sun resides. In this crowded environment, stars experience gravitational forces and accelerations unimaginable anywhere else. They pass close to each other with alarming frequency, and close encounters that would be vanishingly rare in the galactic disk occur regularly, potentially disrupting planetary systems and ejecting stars onto new trajectories. Close encounters and even direct collisions between stars occur far more frequently near the galactic center than in the galactic suburbs where our sun resides safely. While stellar collisions remain rare even at the galactic center, occurring perhaps once every few million years within a given volume, this rate exceeds the collision frequency in the solar neighborhood by factors of thousands or millions. These collisions can create exotic stellar types, merge stars to form more massive objects, disrupt binary systems, and produce unique stellar populations found only in galactic centers. Recent observations have detected binary stars orbiting close to Sagittarius A star, the first time stellar pairs have been confirmed in such an extreme environment, surviving despite the black hole's powerful tidal forces that threaten to tear them apart. The galactic center lies approximately 25,000 to 28,000 light-years from Earth, close enough that astronomers can study individual stars with powerful telescopes, tracking their orbits with precision, measuring their properties in detail, and observing stellar dynamics in this unique environment. Yet this distance is also far enough that dust and gas obscure much of the region from visible light observation, blocking optical wavelengths and hiding the galactic center from traditional telescopes. Infrared and radio observations can penetrate this obscuring material, seeing through the dust to reveal the intense activity occurring near the supermassive black hole, mapping stellar populations, tracing gas flows, and imaging the environment surrounding Sagittarius A star. The Sagittarius C star-forming region, located approximately 300 light-years from Sagittarius A star in projection on the sky, contains an estimated 500,000 stars, visible in recent James Webb Space Telescope observations, along with dense molecular clouds, actively forming new stellar generations even in this harsh environment near the galactic center. This region provides a unique laboratory for studying star formation under extreme conditions, where intense radiation, strong magnetic fields, and powerful tidal forces create challenges for star formation that do not exist in calmer regions, like the Orion Nebula or other stellar nurseries scattered throughout the galactic disk. The stars populating the Milky Way span an extraordinary range of properties, from the tiniest red dwarfs, barely massive enough to sustain hydrogen fusion in their cores, to massive blue giants, hundreds of times more massive and millions of times more luminous than our sun. Understanding this stellar population, its composition, its distribution, and its evolution provides crucial insights into how the galaxy has evolved over billions of years, and how it continues changing today through ongoing star formation, stellar evolution, and the gradual enrichment of the interstellar medium with heavy elements forged in stellar cores. Red dwarf stars, also called M-dwarfs by astronomers who classify stars according to their spectral properties, dominate the galactic census by sheer numbers, comprising roughly 75% of all stars in the Milky Way, according to recent surveys and statistical analyses. These small, cool stars, with masses ranging from about 8% to 50% of the Sun's mass and surface temperatures between 2,300 and 3,800 Kelvin, burn their hydrogen fuel so slowly and efficiently through the proton-proton chain reaction that they can shine for hundreds of billions of years, maintaining stable energy output for timescales far longer than the current age of the universe. Despite their overwhelming numerical dominance, red dwarfs contribute relatively little to the galaxy's total luminosity because each individual star is quite faint, often shining with less than 1% of the sun's brightness, sometimes as little as 1/10,000th. The faintest red dwarfs produce so little light that they remain invisible to the naked eye even if they were located at the distance of Alpha Centauri, our nearest stellar neighbor just 4.37 light-years away. This creates an interesting and somewhat paradoxical situation. Most stars are red dwarfs, but most starlight visible to our eyes comes from rarer, more luminous stars that represent a tiny fraction of the total stellar population. The night sky's brightest stars, the ones that have captured human attention since prehistoric times and earned names in ancient cultures around the world, are almost never red dwarfs, but rather massive, hot blue and white, main-sequence stars like Rigel and Spica, evolved red giants like Betelgeuse and Aldebaran nearing the ends of their lives, or intermediate mass stars in various evolutionary stages. These luminous stars represent the exceptions, the rare massive objects and evolved giants, while the typical star, the overwhelming statistical majority, remains too faint for human eyes to detect without powerful telescopes. At the opposite extreme from red dwarfs are the massive blue giants and supergiants, stars exceeding tens or even hundreds of solar masses, burning so hot and bright that they dominate their surroundings despite their extreme rarity. These stellar behemoths maintain surface temperatures exceeding 30,000 to 50,000 Kelvin, hot enough that their peak emission occurs in the ultraviolet rather than visible wavelengths, and they pour out energy at rates millions of times greater than the sun. Their brilliant blue-white light dominates young stellar clusters, highlights spiral arms where massive stars preferentially form, and creates spectacular nebulae as their intense radiation ionizes surrounding gas, causing it to fluoresce and glow like a cosmic neon sign. Yet these giants are exceedingly rare, representing perhaps 1 in a million stars, or even fewer for the most massive examples, and they are tragically short-lived by stellar standards. A star with 100 solar masses, near the upper limit of what stellar evolution theory suggests can form through normal processes, exhausts its nuclear fuel in just a few million years, perhaps as little as 3 million years for the most massive examples. This cosmic eye blink, brief almost beyond comprehension compared to the sun's 10 billion year lifetime on the main sequence, means these stars live fast and die young, burning through their entire life cycle in less time than it takes our solar system to complete a single orbit around the galaxy. Between the extremes of faint red dwarfs and brilliant blue giants lie stars like our Sun, classified by astronomers as a G-type main sequence star, or yellow dwarf, with a spectral type of G2V indicating its temperature, luminosity, and evolutionary status. Approximately 7 to 8% of Milky Way stars are similar to the Sun in mass, temperature, and luminosity, according to statistical surveys of stellar populations. While this percentage seems small, Representing less than one star in 12, it translates to billions of sun-like stars distributed throughout the galaxy, each potentially hosting planetary systems formed through the same processes that created our solar system, each representing a possible site for the emergence of life and perhaps intelligence. Our Sun itself is approximately 4.6 billion years old, determined through radioactive dating of meteorites and solar system objects that preserve a record of the Sun's formation, making it middle-aged by stellar standards, with roughly another 5 billion years remaining before it exhausts the hydrogen fuel in its core and begins the dramatic evolutionary changes that will transform it into a red giant. For now, the Sun exists in a stable phase, fusing hydrogen into helium through the proton-proton chain, maintaining a careful balance between gravitational collapse and radiation pressure, shining with nearly constant luminosity that has allowed life to flourish on Earth for billions of years. The Milky Way currently forms new stars at a rate of approximately 1 to 3 solar masses per year, meaning the galaxy produces the equivalent of 1 to 3 solar masses per year, 3 sun mass stars annually. Though in reality, star formation creates stars of all masses, from tiny red dwarfs to rare massive giants, following a distribution called the initial mass function. This rate might sound rapid, suggesting the galaxy would quickly exhaust its gas supplies and cease forming stars entirely. But it actually represents a relatively sedate pace compared to starburst galaxies, undergoing intense episodes of star formation, triggered by galaxy collisions, mergers, or other dramatic events that can produce hundreds or even thousands of solar masses of new stars per year. The star formation rate has varied dramatically over the galaxy's history, reflecting changing conditions, varying gas supplies, and the influence of major events like galaxy mergers. Evidence from stellar ages, chemical compositions, and theoretical models suggests peak star formation occurred approximately 10 to 11 billion years ago, following major merger events that supplied fresh gas for making stars, disrupted the young galaxy structure, and triggered intense bursts of stellar birth. Since that peak, the rate has gradually declined as gas supplies have been depleted, though star formation continues today in molecular clouds scattered throughout the disk, maintaining a steady production of new stellar generations. Star formation occurs primarily in dense clouds of gas and dust, called molecular clouds, so named because they are cold and dense enough that atoms combine into molecules, particularly molecular hydrogen, H2, but also carbon monoxide, TCO, water, ammonia, and more complex organic molecules. These clouds can contain thousands to millions of solar masses of material and extend across tens or hundreds of light years, creating vast structures visible as dark patches against the background glow of the Milky Way, blocking starlight from more distant regions. When regions within a molecular cloud become sufficiently dense and cold, typically requiring densities of thousands or millions of hydrogen molecules per cubic centimeter and temperatures just a few tens of degrees above absolute zero, gravity begins to overwhelm the gas pressure that normally supports the cloud, and collapse begins. As material falls inward during cloud collapse, conservation of angular momentum causes the infalling gas to spin faster, forming a rotating disk around the central condensation, similar to how a figure skater spins faster when pulling in their arms. The collapsing core heats up as gravitational potential energy converts to thermal energy, raising temperatures until, when the core reaches roughly 10 million Kelvin, hydrogen fusion ignites. Nuclear reactions begin producing energy. Radiation pressure balances gravitational collapse, and a new star is born. This process rarely produces isolated stars. Instead, molecular clouds typically fragment into many collapsing regions simultaneously, forming clusters of stars that emerge together from their natal cocoon, bound together by their mutual gravity, sharing common origins, ages, and initial compositions. Approximately half or more of all stars in the Milky Way exist in binary or multiple star systems, where two or more stars orbit their common center of mass, bound together by gravity, following each other through the galaxy. Recent surveys using techniques ranging from direct imaging to radial velocity measurements to eclipse observations suggest the binary fraction may be even higher among certain types of stars, with some studies indicating that most Sun-like stars form in binary or higher order multiple systems, though many of these systems are subsequently disrupted by encounters with other stars or cluster dissolution, leaving isolated single stars like our Sun. These binary and multiple star systems range enormously in their properties and configurations. Wide binaries are separated by thousands of astronomical units, so distant from each other that they take millions of years to complete a single mutual orbit, and they barely influence each other's evolution, essentially functioning as independent stars that happen to share common space and motion. Contact binary stars, at the opposite extreme, physically touch each other, sharing outer layers of gas as they orbit their common center of mass every few hours, so close that tidal forces distort them into elongated egg shapes, and mass constantly flows between the two stars, creating complex evolutionary pathways, unlike anything that occurs in single stars. Binary systems play important roles in galactic evolution and stellar astrophysics, particularly when one member exhausts its fuel and begins evolving off the main sequence, while its companion remains on the main sequence, still fusing hydrogen in its core. Mass can transfer from the evolving star to its companion through various mechanisms, including stellar winds that the companion captures, direct transfer through the Lagrange point, where the gravitational fields of the two stars meet, or common envelope evolution, where one star expands to engulf its companion, creating a shared envelope of gas surrounding both stellar cores. This mass transfer can trigger dramatic events, including nova explosions when hydrogen accumulates on a white dwarf companion and ignites, or even supernova explosions in cases where mass transfer pushes a white dwarf over the Chandrasekhar limit of 1.4 solar masses, causing catastrophic collapse and thermonuclear detonation. The composition of stars, the mix of elements they contain, provides crucial insights into galactic evolution and the history of chemical enrichment over cosmic time. The first stars that formed in the early universe, the population 3 stars that have never been directly observed, but whose existence is predicted by theory, and whose influences appear in the compositions of later stellar generations, consisted almost entirely of hydrogen and helium produced in the Big Bang, with essentially zero heavy elements. These primordial stars had no metals in their compositions, where astronomers use metals to mean all elements heavier than helium, a terminology that astronomers find perfectly reasonable, but which often confuses chemists and the general public. As these first generations of stars lived their lives, fused lighter elements into heavier ones through nuclear reactions in their cores, and eventually died in supernova explosions that scattered their enriched material throughout space. They gradually polluted the primordial gas with heavy elements, slowly building up the concentrations of carbon, oxygen, iron, and other elements that make planets and life possible. Each subsequent stellar generation incorporated some of these heavy elements, and in turn added more during their own lives and deaths, creating a gradually accelerating enrichment process that has been operating for the past 13 billion years. By measuring the metal content of stars of different ages, a technique called stellar archaeology, astronomers can trace this chemical enrichment over cosmic time and reconstruct the history of star formation and galactic evolution. The oldest stars, found primarily in the halo and in ancient globular clusters, have metallicities as low as 1/10,000th or even 100,000th of the Sun's metal content, indicating they formed from nearly pristine primordial gas, with only the slightest enrichment from a few previous stellar generations. Intermediate age stars show progressively higher metal content as the interstellar medium became more enriched over time. The youngest stars forming today have metal abundances at or slightly above solar values, reflecting billions of years of cumulative enrichment, and in some cases showing enrichments in specific elements that trace particular nucleosynthetic processes. The European Space Agency's Gaia spacecraft has revolutionized our understanding of stellar populations in the Milky Way, transforming galactic astronomy through precision measurements that were impossible before its launch. Launched in December 2013 and operational since mid-2014, Gaia has measured the precise positions, distances using parallax, and proper motions of nearly 2 billion stars, more than 1% of the galaxy's total stellar population. This represents a staggering expansion compared to observations available before Gaia, when detailed measurements existed for perhaps only 2 to 3 million stars total. And earlier missions like Hipparcos measured parallaxes for only about 100,000 stars with reasonable precision. Gaia has expanded the measurable volume of space by approximately a factor of 100 in radius compared to pre-Gaia surveys, and achieved parallax precisions about 100 times better than previous missions, improving distance measurements from roughly 10% uncertainties to better than 1% for many stars. This combination, expanding the accessible volume by 100 times in each dimension, while simultaneously improving precision by factors of 10 to 100, has created a dataset that contains perhaps 1 million times more information than astronomers had access to before Gaia, fundamentally transforming our to study galactic structure, stellar populations, and the Milky Way's history. This extraordinary dataset has enabled astronomers to construct the most detailed, three-dimensional map of the Milky Way ever created, revealing structure on all scales, from individual star clusters and stellar streams to the overall architecture of the spiral arms and bar, from subtle vertical waves in the disk to the complex distributions of halo stars. Gaia's observations have revealed substructures in stellar populations that were previously invisible, traced the orbits of stars influenced by past galactic collisions, and found signatures of those ancient mergers in present-day stellar distributions, and identified thousands of new binary stars, variable stars, brown dwarfs, white dwarfs, and other special objects, greatly expanding catalogs of unusual and interesting stellar types. Among Gaia's most remarkable discoveries are the remnants of past galactic mergers, recorded in the motions and compositions of halo stars, revealed through a technique sometimes called galactic archaeology. When a smaller galaxy collides with and merges into the Milky Way, a process that has occurred multiple times throughout our galaxy's history, its stars do not immediately mix uniformly throughout the Milky Way's stellar population, but instead retain characteristic orbital patterns, velocity, distributions, and chemical compositions that betray their external origin. These signatures can persist for billions of years, allowing astronomers to identify groups of stars that once belonged to separate galaxies, to reconstruct the orbits and properties of those long-destroyed systems, and to piece together the Milky Way's merger history, one destroyed galaxy at a time. The Gaia-Enceladus collision, also called the Gaia sausage, due to the elongated distribution of stellar velocities it creates in velocity space, represents one of the most significant ancient merger events revealed by Gaia data. This collision occurred approximately 10 to 11 billion years ago, identified through detailed analysis of halo star velocities, orbits, and chemical compositions, when a dwarf galaxy with about 1/4 to 1/3 of the Milky Way's mass at that time collided with and merged into our galaxy in what must have been a catastrophic encounter. The collision was violent enough to send stars onto highly elliptical, radial orbits that carry them far above and below the galactic disk in their journeys around the galactic center, creating unusual orbital distributions, unlike anything produced by stars formed within the Milky Way itself. These merger remnant stars now constitute a significant fraction of the stellar halo, perhaps containing 5 to 10 billion solar masses of stars, according to some estimates, and their unusual orbital patterns create the elongated, sausage-shaped distribution in velocity space that gives this ancient merger its informal name. By studying these stars in detail, measuring their ages, compositions, and kinematics, astronomers have reconstructed what Gaia Enceladus must have been like before its destruction. A substantial galaxy in its own right, with perhaps 10 billion solar masses total, enriched to about 1/10 of solar metallicity, hosting multiple billion years of star formation before its fatal encounter with the Milky Way ended its independent existence and scattered its stars throughout our galactic halo. Not all stars remain gravitationally bound to the Milky Way throughout their existence, despite the galaxy's powerful gravitational pull and the difficulty of achieving escape velocity. Some stars receive gravitational kicks during close encounters with other stars, with stellar clusters, or particularly with the supermassive black hole at the galactic center, accelerating them to velocities exceeding the galaxy's escape speed of roughly 550 kilometers per second at the solar neighborhood. These hypervelocity stars, traveling at speeds sometimes exceeding 1,000 kilometers per second, are moving fast enough to eventually leave the galaxy entirely, becoming intergalactic wanderers that will spend eternity drifting through the void between galaxies, orphaned from their home galaxy, never to return. The vast majority of the Milky Way's mass, roughly 85 to 90% of everything the galaxy contains, remains completely invisible to our telescopes, regardless of what wavelength we observe at, detectable only through its gravitational influence on visible matter, on stars and gas, whose motions reveal the presence of unseen mass. This mysterious substance, which physicists call dark matter, though that name reveals more about our ignorance than about the substance itself, permeates the galaxy in an enormous halo, extending far beyond the visible disk, reaching out hundreds of thousands of light years in all directions, dominating the galaxy's gravitational potential, and fundamentally shaping its structure and evolution. When astronomers calculate the total galactic mass, they arrive at a figure of approximately 1.5 trillion solar masses, according to recent estimates, though this number carries substantial uncertainty and different measurement methods sometimes yield somewhat different results. This tremendous mass, about 1,500 times the mass of our Sun, multiplied by 1 billion, greatly exceeds what we can observe directly. All the stars in the Milky Way, those hundreds of billions of individual suns, contribute perhaps 60 to 100 billion solar masses to this total. All the gas and dust, the raw materials for future star formation, add perhaps another 10 to 20 billion solar masses. Everything we can detect with telescopes, observing any wavelength of light, from radio waves to gamma rays, accounts for only about 10 to 15% of the galaxy's total mass, leaving 85 to 90% unaccounted for by visible matter. The first compelling evidence for dark matter's existence came from studying how galaxies rotate, pioneering work conducted in the 1970s and 1980s, though hints appeared in earlier observations that were not fully appreciated at the time. Astronomer Vera Rubin, working at the Department of Terrestrial Magnetism at the Carnegie Institution, conducted groundbreaking observations of spiral galaxies using spectroscopy to measure rotation speeds of stars and ionized gas at various distances from galactic centers. According to Newton's laws of gravity and orbital motion, which had been tested and confirmed countless times throughout the solar system, objects farther from a gravitating mass should orbit more slowly, following Kepler's third law, just as outer planets in our solar system orbit the Sun more leisurely than inner planets, taking decades or centuries to complete orbits that inner planets finish in months or years. Rubin and her collaborators expected to see rotation speeds decrease with distance from galactic centers, with stars in outer regions moving more slowly than those closer in, eventually falling to low velocities in the sparse outer reaches of galactic disks. Instead, they found something completely unexpected and revolutionary. The rotation speeds remained roughly constant even at great distances from the centers, out to the edges of the visible disks and beyond, creating what astronomers call flat rotation curves. This observation implied that galaxies must contain far more mass than their visible components could possibly account for, and this extra mass had to be distributed differently than the visible matter, extending far beyond the visible edges in a vast halo to maintain those high rotation speeds at large radii. The Milky Way's rotation curve shows the same flat behavior that Rubin observed in external galaxies, providing direct evidence that our own galaxy is embedded in a dark matter halo just like those other spirals. When astronomers measure the orbital velocities of stars at various distances from the galactic center, using techniques ranging from proper motion measurements of nearby stars to radial velocities of more distant objects, to the kinematics of satellite galaxies orbiting in the halo, they can apply basic physics to calculate how much total mass must be present at various radii to generate the gravitational forces required to maintain those observed velocities. The answer consistently indicates that visible matter accounts for only a small fraction of the total mass required to explain the observations. The dark matter halo extends far beyond the stellar disk, reaching outward perhaps 600,000 to 900,000 light-years, or even farther from the galactic center, according to various estimates, though the halo's exact extent remains poorly constrained because measuring properties at such great distances proves extremely challenging. At these enormous distances, 5 to 10 times farther out than the visible disk's edge, the dark matter density drops to very low values, but the total mass contained remains substantial because of the vast volumes involved. Eventually, at radii approaching 1,000,000 light-years, the Milky Way's dark matter halo begins to overlap with the dark matter halos of nearby galaxies including Andromeda, creating a complex cosmic web of gravitational influence where defining exactly where one galaxy ends and another begins becomes ambiguous and dependent on arbitrary definitions. Recent research using classical Cepheid variable stars has provided new insights into the shape and properties of this dark matter halo, exploiting these pulsating stars as distance indicators and tracers of galactic structure. Cepheids are evolved stars that pulsate regularly, expanding and contracting, brightening and dimming, with periods ranging from days to months, and their intrinsic brightness relates directly to their pulsation period through a relationship called the period luminosity relation. This relationship, discovered by Henrietta Leavitt in 1908 through observations of Cepheids in the small Magellanic Cloud, allows astronomers to determine distances to Cepheids by measuring their pulsation periods and apparent brightnesses, making them powerful tools for mapping galactic structure. A 2024 study, published in the monthly notices of the Royal Astronomical Society, used careful observations of Cepheid stars at various locations throughout the Milky Way to probe the distribution of matter, both visible and dark, throughout the galaxy. The researchers found that the Milky Way's dark matter halo is slightly oblate, meaning it is somewhat flattened rather than perfectly spherical, compressed along one axis like a slightly squeezed ball. The halo has a flattening ratio, defined as the ratio of the shortest to longest axis, between 0.84 and 0.96, according to their analysis, where a value of 1.0 would represent a perfect sphere and smaller values indicate greater flattening, more deviation from spherical symmetry. This oblate shape suggests the dark matter halo rotates slowly, with its rotation axis aligned roughly perpendicular to the galactic disk's plane, spinning in the same sense as the disk rotation, but much more slowly, taking far longer than the disk's roughly 250 million year rotation period to complete one turn. The halo's rotation and flattening provide important constraints on dark matter's properties and on theories of galaxy formation, helping distinguish between different dark matter candidates and formation scenarios. Though many fundamental questions about the halo's detailed structure, its formation history, and its relationship to the visible galaxy remain open and actively researched. What is dark matter actually made of? This question, deceptively simple to ask, represents one of the deepest and most frustrating mysteries in all of physics, a puzzle that has resisted solution despite decades of intensive theoretical and experimental work. Dark matter does not emit, absorb, or reflect electromagnetic radiation of any wavelength that we can detect, making it completely invisible to all conventional telescopes, whether they observe radio waves, infrared light, visible light, ultraviolet, X-rays, or gamma rays. It does not interact with normal matter through electromagnetic forces, the forces responsible for chemistry and most everyday phenomena, nor through the strong nuclear force that binds atomic nuclei together, passing through ordinary matter as if it were not there, like a ghost moving through walls. The only force we definitively know dark matter responds to is gravity. And gravity is precisely what revealed dark matter's existence in the first place, through its effects on galactic rotation curves, gravitational lensing, and cosmic structure formation. Dark matter plays an absolutely crucial role in galaxy formation and evolution throughout cosmic history, acting as the gravitational scaffolding upon which visible galaxies are built. In the early universe, in the first few 100,000 years after the Big Bang, before atoms even formed, dark matter began clumping together under its own gravity, forming small concentrations that grew over time through gravitational attraction. Normal matter could not collapse at these early times because radiation pressure from the intense background photons filling the universe kept it smooth and diffuse, preventing density fluctuations in normal matter from growing. Dark matter, immune to electromagnetic interactions and therefore unaffected by radiation pressure, could collapse freely, creating gravitational potential wells, regions of enhanced gravity that grew deeper over time. Eventually, after the universe cooled sufficiently that electrons and protons combined to form neutral hydrogen atoms in an event called recombination, occurring about 380,000 years after the Big Bang, normal matter became transparent to radiation, decoupled from the photon bath, and could finally respond to gravity and begin falling into the potential wells created by dark matter. This normal matter, primarily hydrogen and helium gas, fell into the dark matter concentrations, accumulated in the centers of dark matter halos, eventually became dense enough to form stars, and created the first galaxies. Without dark matter providing the initial gravitational seeds, without those pre-existing potential wells for normal matter to fall into, the universe might have remained nearly smooth and structureless for far longer, delaying galaxy formation by billions of years, or possibly preventing it entirely. The Milky Way's formation history stretches back nearly to the very beginning of cosmic time itself, to an era when the universe was less than 1 billion years old, and very different from the cosmos we observe today. In those early times, perhaps 100 to 200 million years after the Big Bang, once the first stars began to ignite, but long before galaxies like the Milky Way existed in their present form, the cosmos consisted of small clumps of dark matter surrounded by primordial gas composed almost entirely of hydrogen and helium, with trace amounts of lithium, but essentially nothing else. No heavy elements, no carbon or oxygen or iron or any of the elements that make planets and life possible. The proto-Milky Way began not as a single coherent structure, but as a collection of smaller clumps of dark matter and gas that gradually merge together through what cosmologists call hierarchical assembly, a bottom-up process where small structures form first and then merge to create progressively larger objects over billions of years. This merger-driven growth represents a fundamental prediction of the standard cosmological model, arising naturally from the way gravity amplifies initial density fluctuations and pulls matter together into ever larger concentrations. Evidence for this merger history comes from multiple sources, including the chemical signatures of stars in different galactic components, the unusual orbital properties of halo stars that reveal their origins in now destroyed satellite galaxies, the detection of stellar streams wrapping around the galaxy that trace the tidal disruption of smaller systems, and computer simulations that reproduce observed galactic properties only when including multiple ancient mergers. Throughout its long history spanning more than 13 billion years, the Milky Way has been essentially a cosmic cannibal, consuming smaller galaxies that ventured too close to its gravitational domain, growing through accretion and merger, adding their stars to its own population, and gradually increasing in mass from a much smaller progenitor to the massive spiral galaxy we observe today. This process continues in the present epoch, observable in real time, providing astronomers with live examples of galactic cannibalism in action. The Sagittarius Dwarf Elliptical Galaxy, a small elliptical galaxy discovered only in 1994, despite its relative proximity because it lies hidden behind the galactic bulge from our perspective, is currently being torn apart by the Milky Way's powerful tidal forces. Its stars are being stripped away through gravitational interactions and distributed in long streams that wrap around our galaxy multiple times. Eventually, these stars will become indistinguishable members of the Milky Way's halo, all memory of their separate origin erased except for subtle signatures in their chemical compositions and orbital properties. The Large Magellanic Cloud and Small Magellanic Cloud, visible as fuzzy patches in the southern sky from locations south of the equator and appearing almost like detached pieces of the Milky Way to casual observers, are dwarf galaxies currently orbiting our galaxy as satellites, bound to us by gravity but maintaining separate identities, at least for now. The Large Magellanic Cloud, located approximately 160,000 light-years from Earth and containing roughly 30 billion stars, along with substantial quantities of gas and dust, represents one of the most massive satellite galaxies orbiting the Milky Way. The Small Magellanic Cloud, lying about 200,000 light-years distant, hosts approximately 3 billion stars in a more irregular structure. As these satellites orbit, they interact gravitationally with each other and with the Milky Way, creating tidal streams of stars and gas that trace their orbital paths through space, and they will eventually be consumed entirely by the Milky Way over the next several billion years, adding their mass to our galaxy's growing bulk. 3 million light-years away, officially measured at approximately 2.5 million light-years distance, moving through the darkness of intergalactic space at approximately 110 kilometers per second, the Andromeda Galaxy approaches us on what may be a collision course. This majestic spiral galaxy, the largest member of our local group, and containing perhaps 1 trillion stars, according to recent estimates, is approaching the Milky Way at a rate that will close the distance between our galaxies dramatically over the next few billion years. For decades, astronomers have predicted that these two massive galaxies would inevitably collide in approximately 4 billion years, eventually merging over the following several billion years to create a single giant elliptical galaxy that some astronomers have informally nicknamed Milkomeda, in anticipation of this future cosmic union. However, a 2024 study using the latest data from the Gaia spacecraft, combined with Hubble Space Telescope measurements, has revealed that the cosmic future may be more uncertain than previously thought, with calculations suggesting there is only about a 50% chance that the Milky Way and Andromeda will actually collide directly, rather than executing a close flyby or entering into a long-term orbital dance before any eventual merger. If the galaxies do collide as traditionally predicted, individual stars will likely survive the encounter relatively unscathed, despite the dramatic reshaping of the galactic structures. The distances between stars are so vast compared to stellar sizes that direct stellar collisions will be extraordinarily rare, with perhaps only a handful occurring throughout the entire merger, despite the hundreds of billions of stars involved. Our Sun and its planets, if they still exist in any habitable form billions of years hence, face an uncertain future in this collision, with computer simulations suggesting approximately a 50% probability that the solar system will be ejected to regions much farther from the merged galaxy's center, possibly into the sparse halo, and a small chance of perhaps 2 to 3% that the solar system could be ejected from the merged galaxy entirely, becoming an intergalactic wanderer drifting through the void between galaxies for eternity. The discovery that planets are common throughout the Milky Way represents one of the most profound shifts in human understanding of our place in the cosmos. For most of human history, we knew of only a few planets, those visible to the naked eye orbiting our Sun, and speculation about whether other stars hosted similar systems remained purely philosophical. The first confirmed exoplanet orbiting a Sun-like star was discovered in 1995 when Swiss astronomers Michel Maillot and Didier Queloz detected 51 Pegasi b using the radial velocity method, measuring the subtle wobble induced in the parent star by an orbiting planet's gravity. This discovery revolutionized astronomy, earning Mayer and Queloz the 2019 Nobel Prize in Physics, and opened a new field of research that has exploded over the subsequent decades. Since that pioneering discovery, barely 3 decades ago, the field of exoplanet science has grown at an astounding pace. As of late 2024, astronomers have confirmed more than 5,700 exoplanets in over 4,200 planetary systems, according to the NASA Exoplanet Archive, with thousands of additional candidates awaiting confirmation. These discoveries come from multiple detection methods, each with particular strengths and limitations, each biased toward finding certain types of planets in certain orbital configurations, but together painting an increasingly complete picture of planetary demographics throughout the galaxy. NASA's Kepler Space Telescope, which operated from 2009 until its retirement in 2018, after exhausting the fuel needed to maintain its orientation, revolutionized exoplanet science through its transit photometry survey. Kepler monitored more than 150,000 stars simultaneously and continuously for years, watching for the slight dimming that occurs when a planet passes in front of its star from our perspective, blocking a tiny fraction of the starlight. The mission discovered more than 2,600 confirmed exoplanets and thousands of candidates, dramatically expanding humanity's knowledge of planetary systems and revealing that planets are extraordinarily common throughout the galaxy. Kepler's statistical analysis revealed that nearly every star in the Milky Way hosts at least one planet on average, transforming planets from rare curiosities into common cosmic features. This simple statement carries profound implications. If the galaxy contains between 100 and 400 billion stars, and essentially all of them host planets, then the Milky Way contains hundreds of billions or even trillions of worlds, a population of planets that exceeds our ability to observe individually, but that must exist based on statistical extrapolation from the samples we have detected. Among these countless worlds, particular interest focuses on planets in their stars' habitable zones, the range of orbital distances where temperatures allow liquid water to exist on planetary surfaces. Water is essential for all life as we know it, making habitable zone planets prime candidates in the search for extraterrestrial life. The habitable zone's location depends on the star's temperature and luminosity, with cooler stars having closer-in habitable zones and hotter stars having more distant ones. For a Sun-like star, the habitable zone extends roughly from 0.95 to 1.7 astronomical units, encompassing Earth's orbit comfortably within its boundaries, but excluding Venus as too hot and Mars as marginally too cold. Kepler data suggests that between 20 and 50% of Sun-like stars host at least one rocky planet, meaning a planet with a solid surface rather than a gas giant, in their habitable zones. Taking a conservative estimate of 25%, this implies there could be tens of billions of potentially habitable planets orbiting Sun-like stars alone in the Milky Way. If we expand this calculation to include red dwarf stars, which are far more numerous than Sun-like stars, and which also possess habitable zones, albeit at much closer orbital distances, the number of potentially habitable worlds could reach 40 billion or more throughout our galaxy alone. The diversity of exoplanets discovered exceeds what early theories of planet formation predicted. Hot Jupiters, gas giant planets orbiting extremely close to their stars with orbital periods of just days, and surface temperatures hot enough to vaporize metals, were completely unexpected when first discovered, but have proven relatively common in exoplanet surveys. These worlds challenge formation theories that suggested giant planets could only form in the cold outer regions of planetary systems beyond the snowline where water ice can exist, requiring new models involving planetary migration, where planets form at larger distances and then spiral inward to close orbits. Super-Earths, rocky planets with masses between Earth and Neptune, represent another common planetary type with no analog in our solar system. These worlds, with masses typically between 2 and 10 times Earth's mass, and radii between 1.2 and 2.0 times Earth's radius, appear to be among the most common planets in the galaxy based on Kepler statistics. Their properties remain somewhat mysterious because we have no local examples to study in detail, and their habitability remains an open question depending on whether they retain thick hydrogen atmospheres like mini-Neptunes or possess rocky surfaces with thinner atmospheres more conducive to life. The James Webb Space Telescope, launched in December 2021 and beginning science operations in mid-2022, has opened new possibilities for characterizing exoplanet atmospheres in unprecedented detail. JWST observes in infrared wavelengths, where the contrast between planets and their host stars is more favorable than in visible light, and its large mirror and sensitive instruments allow it to measure the spectra of light filtering through planetary atmospheres during transits. By analyzing these transmission spectra, astronomers can identify molecules present in exoplanet atmospheres, searching for biosignatures like oxygen, methane, and other gases that might indicate the presence of life. While definitive biosignature detections remain elusive as of late 2024, JWST's capabilities bring this goal within reach for favorable targets, particularly planets orbiting small, cool stars, where the planet-to-star contrast is most favorable. Each new observation adds to our understanding of exoplanet atmospheres, revealing their compositions, temperatures, cloud properties, and chemical dynamics, gradually building toward the capability to detect signs of life beyond Earth if such signatures exist and are detectable with current technology. The Milky Way rotates differentially, with different parts of the galaxy orbiting the galactic center at different angular velocities, unlike a solid wheel that rotates rigidly with all parts completing one rotation in the same time. This differential rotation reflects the galaxy's nature as a gravitationally bound system, where each star follows its own individual orbit determined by the total gravitational potential at its location. In the inner galaxy, orbital periods are short, measured in tens of millions of years, while in the outer galaxy, orbits take hundreds of millions of years to complete. Our solar system orbits at a velocity of approximately 220 to 240 kilometers per second, relative to the local standard of rest, the reference frame defined by the average motion of stars in our neighborhood. This velocity, sustained continuously as we circle the galaxy, means we are moving at roughly 500,000 miles per hour through the galaxy, fast enough to circle Earth's equator in about 3 minutes, yet so slow compared to the vast scale of the galaxy that completing one orbit takes 225 to 250 million years. The solar system's path through the galaxy is not a simple circle, but a complex trajectory influenced by the gravitational potentials of the disk, bulge, bar, and dark matter halo. We oscillate vertically through the galactic plane with a period of approximately 70 million years, passing through the disk midplane where stellar and gas density peak every 35 million years or so, then rising above the plane, reaching maximum height, falling back down, passing through the midplane again, headed in the opposite vertical direction, descending below the plane, and then rising once more to complete the cycle. Currently, we are located about 95 light-years above the galactic plane and moving upward toward the peak of our vertical oscillation. Stellar orbits throughout the galaxy reflect their origins and histories. Thin disk stars like the Sun follow nearly circular orbits confined close to the galactic plane with small vertical oscillations, their orderly motion reflecting formation from a settled rotating disk. Thick disk stars have less circular orbits with larger random velocities and greater vertical excursions, their properties indicating formation during more chaotic periods or origins in disrupted satellite galaxies. Halo stars follow highly elliptical orbits at all inclinations, plunging through the disk and rising to great heights in the halo, their unusual kinematics proving their origins in external galaxies that merged with the Milky Way billions of years ago. The spiral arms, those beautiful sweeping curves that define the galaxy's appearance, are density waves rather than material structures, patterns that persist even as individual stars and gas clouds move through them. Stars enter arms from one side, slow down as they experience enhanced gravity in the denser regions, participate in the arm structure for tens of millions of years, and then exit from the other side to continue their orbits, the arm pattern rotating at a different rate than the stars themselves. This density wave picture, supported by observations and theoretical models, explains how spiral structure persists over billions of years, despite differential rotation that would otherwise destroy it. Recent measurements using Gaia data have revealed subtle features in the galactic disk, including vertical waves, ripples, and other disturbances that result from past interactions with satellite galaxies. These discoveries demonstrate that the Milky Way is not a static equilibrium system, but a dynamic structure still responding to ancient perturbations and ongoing interactions with satellites, constantly evolving on timescales of hundreds of millions of years, slowly changing its structure and properties, even as it maintains its basic spiral architecture. As we draw our journey through the Milky Way to a close, we find ourselves with a deeper appreciation for this cosmic structure we call home. We have explored 100 facts about our galaxy, each revealing something fundamental about its nature, structure, history, or future. We have learned that the Milky Way is a barred spiral galaxy spanning 100,000 light-years, containing hundreds of billions of stars and planets, dominated by invisible dark matter that outweighs visible matter by factors of nearly 10, shaped by billions of years of evolution, including multiple major mergers, and destined for a potential future collision with Andromeda that may transform both galaxies. We have ventured to the galactic center to observe Sagittarius A star, the supermassive black hole whose existence was confirmed through decades of observations and recently imaged directly by the Event Horizon Telescope. We have counted stars and found that red dwarfs dominate numerically, while rare massive stars dominate the light we see. We have explored the invisible dark matter halo, extending far beyond the visible disk, providing the gravitational scaffolding that holds the galaxy together and prevents it from flying apart despite its rapid rotation. We have looked backward billions of years to witness the galaxy's formation through mergers and hierarchical assembly, uncovering evidence of ancient collisions preserved in stellar populations today. We have looked forward billions of years to contemplate the potential collision with Andromeda. We have discovered that planets are extraordinarily common, with potentially tens of billions of habitable worlds scattered throughout the galaxy, raising profound questions about whether life and intelligence have arisen elsewhere among those countless worlds. The Milky Way reminds us that we are part of something far larger than ourselves, connected to this cosmic structure through the very atoms that compose our bodies. Every atom heavier than hydrogen and helium in your body, the carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron in your blood, was forged in the core of a star that died billions of years ago, scattered through supernova explosions, mixed into molecular clouds, and eventually incorporated into the disk of gas and dust that formed our solar system. We are quite literally made of stardust, cosmic recycling made manifest in living, thinking beings who can contemplate the very stars from which they came. Yet for all we have learned about the Milky Way over centuries of observation and decades of intensive study with modern instruments, profound mysteries remain. Dark matter's fundamental nature eludes us despite overwhelming evidence for its existence and despite its dominance of the galactic mass budget. We do not know whether life exists elsewhere in the galaxy, whether the billions of potentially habitable planets host actual biospheres, whether intelligence is common or vanishingly rare, whether we are alone or one civilization among multitudes. We cannot predict with certainty whether the Milky Way will collide with Andromeda or execute a near miss. The detailed formation history, the precise number and timing of past mergers, the mechanisms that drive spiral structure, and countless other questions await future generations of astronomers armed with more powerful instruments and new observational techniques. These remaining mysteries provide motivation for continued exploration and study. New telescopes, both ground-based and spaceborne, promise to reveal the Milky Way in ever greater detail. The James Webb Space Telescope peers through cosmic dust to observe the earliest stages of star formation in molecular clouds. Future space-based gravitational wave observatories will detect merging black holes and neutron stars throughout the galaxy, providing new windows into compact objects and extreme physics. Improved dark matter detection experiments continue searching for these elusive particles, and the search for biosignatures in exoplanet atmospheres may finally answer humanity's ancient question about whether we are alone in the universe. The Milky Way also provides a template for understanding galaxies throughout the universe. While each galaxy is unique with its own particular history and characteristics, the physical processes operating in the Milky Way apply universally. Star formation, chemical evolution, black hole growth, spiral structure formation, dark matter halos, and all the other phenomena we observe locally also occur in galaxies billions of light years away. By studying our own galaxy in extraordinary detail, impossible for any external galaxy, we gain insights applicable across cosmic distances, making the Milky Way a crucial laboratory for understanding galactic physics throughout the universe. Perhaps most importantly, the Milky Way inspires wonder and contemplation. On a dark, clear night far from city lights, when you can see the galactic band stretching across the sky from horizon to horizon, you are witnessing something that has inspired humans since our ancestors first gazed upward in contemplation. Ancient peoples saw divine rivers, celestial pathways, and cosmic legends written in that pale glow. Today, armed with scientific understanding, built through centuries of patient observation and analysis, we see something arguably even more magnificent. Billions of stars like our sun, trillions of worlds, supermassive black holes, dark matter halos, spiral arms traced by massive stars. The combined light of hundreds of billions of stellar nuclear furnaces, all bound together by gravity into a structure so vast it takes light 100,000 years to cross it. Every galaxy we observe, from the nearest dwarf irregulars to the most distant spirals visible only through the most powerful telescopes, shares a common nature with our Milky Way. They are all gravitationally bound collections of stars, gas, dust, and dark matter, each hosting millions or billions or trillions of stars, each potentially harboring life and intelligence, each with its own unique history and future. The universe contains hundreds of billions of galaxies, according to current surveys and estimates, each one potentially as complex and interesting as the Milky Way, each one a cosmic structure deserving of study and contemplation. Yet among all those countless galaxies scattered throughout the observable universe, the Milky Way is special to us because it is ours. It is the only galaxy we can study from within, the only galaxy whose stars we can resolve and study individually across vast expanses, the only galaxy where we can trace individual stellar orbits and measure precise distances to tens of thousands of light years, the only galaxy where we can map structure on all scales, from star clusters to spiral arms, using parallax, proper motions, and detailed spectroscopy. This unique perspective makes the Milky Way invaluable as a laboratory for understanding galactic physics, providing insights and constraints impossible to obtain for any external galaxy. Looking toward the future, humanity's relationship with the Milky Way may evolve in unexpected ways. Perhaps one day our descendants will venture to other star systems, spreading through the galactic neighborhood and eventually colonizing portions of the galaxy, transforming us from a single planet species into a truly galactic civilization. Perhaps we will encounter other intelligent civilizations, also exploring their corners of the galactic disk, making contact with alien minds that arose independently elsewhere among those billions of potentially habitable worlds. Perhaps we will develop technologies allowing us to observe the Milky Way from outside, sending probes beyond the galaxy's boundaries to view our home from the external perspective we currently achieve only by observing other galaxies. Even if we never leave the solar system, confined to our tiny corner of space by the vast distances and enormous energies required for interstellar travel, our understanding of the Milky Way will continue deepening with every new observation and theoretical advance. Each discovery adds to the accumulated knowledge we have built about our galaxy over generations of patient scientific work. We live in an extraordinary time, perhaps the first era in human history, when we can truly comprehend the Milky Way's nature, structure, dynamics, and our place within it. This understanding represents one of humanity's great intellectual achievements, the product of centuries of observations, measurements, theoretical work, and the gradual refinement of ideas through the scientific process. As you rest tonight, if you are fortunate enough to see the Milky Way stretching across a dark sky, take a moment to contemplate what that pale band truly represents. You are looking at the combined light of hundreds of billions of stars, most too distant and faint to distinguish individually with unaided eyes. You are seeing across thousands of light years through the galactic disk, observing photons that began their journeys from distant stars before recorded human history began, traveling through space for millennia before finally reaching your eyes. You are gazing upon the galaxy that gave birth to our solar system 4.6 billion years ago, that has hosted our world throughout the entire history of life on Earth, and that will remain home to our descendants for billions of years to come, unless they one day venture to the stars. The Milky Way is not merely a collection of stars, gas, dust, and dark matter, not simply an object for scientific study and astronomical research. It is our cosmic address, our place in the universe, the structure that defines our astronomical context and our relationship to the wider cosmos. Understanding the Milky Way means understanding ourselves, our origins traced back through stellar generations to the Big Bang itself, our present circumstances as one planet among trillions, in a galaxy among billions, and our future, whether confined to one world or spread among the stars. If you have enjoyed this journey through our galactic home, exploring 100 facts about the Milky Way and the remarkable structure it represents, please consider liking this video and subscribing to Astroverse 120 for more explorations of the cosmos. Share your thoughts about the Milky Way in the comments below. What aspect of our galaxy fascinates you most? What questions would you like to see explored in future videos? Which of these 100 facts surprised you or changed how you think about our place in the cosmos? Your engagement, your questions, your curiosity helps this channel continue, bringing the wonders of astronomy to viewers around the world, spreading knowledge and inspiring wonder one video at a time. The universe is vast, almost beyond comprehension, filled with hundreds of billions of galaxies, each containing billions or trillions of stars, scattered across distances measured in billions of light years. Yet among all those countless galaxies, among all those inconceivable multitudes of stars and worlds, we live in the Milky Way. For tonight, for this moment, for our entire existence, past and future, that makes it the most important galaxy in the universe. It is our home, our origin, our context, the stage upon which the drama of human existence has played out and will continue playing out for as long as humanity endures. Sweet dreams and clear skies.